Welcome to the video podcast regarding kinetics and chemistry here at Ontario High School. We're going to be dealing with these aspects of kinetics in today's podcast: reaction rates, rate order determination, and the rate constant. Two major areas of kinetics: reaction mechanisms and what happens to the value of the rate constant when temperature changes will be addressed in a subsequent podcast. But for today, reaction rates, rate order determination, and the rate constant. Welcome. The reaction rate is best described as a measure of how fast a chemical reaction proceeds. This is expressed in terms of either the rate at which a reactant disappears as the reaction proceeds or the rate at which a product appears. We usually measure this in terms of a change in molar concentration, molarity at the beginning to molarity at the end. But it can also be measured when you're dealing with gases in terms of a change in pressure. Let's look at a hypothetical reaction. Here A yields B, and we're going to measure the reaction rate in terms of the disappearance of the reactant A. So our equation is that our rate is equal to the opposite of the change in the molar concentration of A divided by the change in time over which this is measured. When we do this, the units will be measured in moles per liter per second. And the one thing you'll notice about this equation, there is a negative sign in front. Because the change in concentration will be negative, you have a smaller final concentration minus a larger initial concentration, there has to be a negative sign set in front of that ratio so that the rate will appear as a positive number. The rate cannot be negative. We'll examine this same reaction, A yielding B, from the perspective of the appearance of a product. Here we have the rate is equal to the change in the molar concentration of B divided by the change in time. There's no need for a negative sign here because the concentration of B will be increasing with time, so the rate will be positive. Let's look at a sample problem. Consider the following reaction. Here we have 2A plus B yields 3C plus D. And there's a chart here that gives time, gives the concentration of A and the concentration of C. You can see A as a reactant starts out at 2 moles per liter. Remember, when you see a chemical symbol inside a pair of brackets, it's automatically assumed to be a molar concentration or moles per liter. And you can see at the beginning of the reaction at time 0, A is 2 moles per liter. By the time we stop studying this at 30 seconds, A is 1.125 moles per liter. C at the beginning as a product is 0 moles per liter. At 30 seconds it will be at 1.3125 moles per liter. Now, the problems for kinetics are long, and oftentimes they're going to take more than one slide to ask. So it would probably be good if you would pause the podcast at this point, write down the information from this slide before you resume and go on to the next one. Thanks. We're going to use the information from the data table on the previous slide to calculate the rate of the reaction using both the disappearance of the reactant A and the appearance of the reactant C. One thing you will notice is that I'm going to use the initial time increments from 0 to 10 seconds to calculate these, because it is best when you're looking at a reaction rate to try and start as close to what the original concentration was as you can. Now, for A, we take our rate is equal to the opposite of the change in the molar concentration, which is 1.5 moles per liter at 10 seconds, minus 2 moles per liter at the beginning at 0 seconds. And on the bottom we have our change in time is 10 seconds. And you'll notice also I brought down the stoichiometric coefficient from the balanced equation, and it is necessary that you do this. You must have the stoichiometric coefficient if it's anything other than 1 in this rate equation. So our rate again is the opposite of 1.5 moles per liter minus 2 moles per liter divided by 2 times the 10-second time increment, and we get as a rate our 0.025 moles per liter times a second. Well, we've already calculated this rate of reaction based on the disappearance of A. We're going to go ahead and calculate it based on the appearance of C. So here we have our rate is equal to the change in concentration of C, which is 0.75 moles per liter minus its beginning concentration of 0 moles per liter, divided by its stoichiometric coefficient of 3 from the balance equation, times 10 seconds of time increment. So notice there is no negative sign here because this value is positive in itself, because the change in concentration is a positive number with the product. So the 0.75 moles per liter minus 0 moles per liter divided by 30 seconds gives us a reaction rate of 0.025 moles per liter times seconds. This is the end of part 1 of the Kinetics series. I want to leave you with a quote from Winston Churchill: "An appeaser is one who feeds a crocodile hoping it will eat him last." Stay tuned for part 2.